recently, she saw her first ever cricket match in Melbourne with Di Cook. Everyone, please welcome to the stage, Emily.
Thank you so much, Jared. I had the wonderful opportunity this past February to visit the Australia Research Council for 3 weeks, thanks for generous funding from ACEMS, which is the Australian Research Council Centre of Excellence for Mathematical and Statistical Frontiers. And so this is a grant that Di Cook and I received, as well as big thanks to my boss, Chris Valinsky, who let me go. And so this work visualizing multivariate spatiotemporal data was inspired by one of my projects at AT&T, where you can imagine this type of data is abundant and really important for applications like monitoring or our network performance. And so for the project that Di and I are working on, that has since been taken over by Weihao Li, who's an honors research student, and has expanded it significantly for his thesis this year. The work that we have been doing has focused on the Australia wildfires of this past season from 2019 to 2020. So this was devastating in its severity and its spread. It made international headlines for the significant damage to property, to wildfires, to wildlife, as well as the impacts on cities like Melbourne, where the air quality was very, very poor. The benefit to working with data like this is there is so much open data accessible to study the relationships between variables that may impact the bushfire spread. So, you know, these are the summer in Australia goes from about December to February. And so those are some of the hottest months where things like lightning strikes can really rip through forest areas that are inaccessible to fire stations and things like that. And so visualization of this data is itself really interesting because of the scale of the resources that we have to compare it to things like vegetation, the fire stations, how far it is from resources, water, all those sorts of things, as well as historical information on what caused the fire. So there are actually people who, after a season, compile the logs from what was the expected cause, whether that was lightning strike or human error. And you can imagine that between urban and rural, the causes may be very different. But it's not really ideal to only have that for historical data, especially when these wildfires are happening. The ability to predict fire risk for an area has the impact for potential policy to prevent major fires in the future. And so that's what we're looking at here, is what is the visualization that we can consider that combines these sources of data in a way that enables data analysis and EDA for a fire prediction risk model. So to do that, instead of using the historical log data that we, as of right now, I think only have available up to August of 2019, instead what we can use is the Himawari 8 hotspot data, which is a Japanese weather satellite that essentially measures how hot the surface of the Earth is. And pixels are classified as hotspots if they are particularly high in a variable called firepower. And so I sort of think of it as heat radiance. And so there certainly can be pixels that show up as hot based on things like chimneys, volcanoes, but that's sort of the data that we have to work with. And so what we have here is a map of Victoria. And so from that hotspot data, over the 6 months we're considering, there are almost 76,000 hotspots detected in the state of Victoria. So Melbourne is right down here, if you're curious. So we filtered to firepower greater than 100 to sort of filter out those things that might not actually be fires. And that being said, though, we want to be able to track fires. And so I want to note first that this is a bad map for a lot of reasons explained very nicely in this article that I included here. Namely, looking at 6 months of spatial data is not fantastically helpful. It also makes it look like all of Victoria is on fire at some point. And this isn't helpful because we want to be able to parse out when are fires happening and where. And the hotspots themselves, you may have a cluster of hotspots that in layman's terms is the same fire that here appears as multiple fires. So the first thing that we did to process this data was consider how to cluster those hotspots. So we do a spatiotemporal clustering of hotspots that we're writing up for a forthcoming paper. But the key idea is that we look at discrete buckets of time and hotspots that are within a certain distance of each other and create these connected component graphs such that we can consider how they change from one time point to the next. We then calculate the centroid of hotspots in any 1 hour and consider that to be the fire's location at time t sub n. So here's an example of just over the course of several hours, what these fires, these individual clusters look like over time, and you can sort of see how they move and morph and grow. So now, once we have those clusters, we are able to take those 76,000 distinct hotspots and cluster them into 2,000 distinct fires. And so now I've just plotted the ignition points so that we don't have fires that are represented multiple times. And I've also faceted these by month. So small multiples is always a really nice way to get started if you're trying to splice up a spatial thing by time. And so that's what we've done here. And immediately, there's kind of a nice realization that the distribution is very different in October than it is in December and January. In particular, what turns out to be happening here, and what this, if you go and look into this, like why is that the case? It turns out that there is sort of regulated burning off of brush, and where you're allowed to have campfires and things. And that period ends at the end of October. What you're seeing over here in December and January, these are some of the state parks and really big forest areas that are a result of the heat and the lightning and things like that that occurred over the course of the summer. So I just want to mention at this point, there is a huge spectrum between simple data analysis and visualization when you are trying to get a sense of a data set you're working that you think has a spatial component versus like a really slick visualization dashboard where you work with spatial data all the time and this is your jam. And I would say that when I started this project, I was solidly in the first category. And for the purpose of this talk, that's kind of who I'm speaking to. So sometimes you just want to get points on a map. You just want to be able to see patterns and understand relationships with other variables in such a way that enables you to grow your model or inform the variables that you're choosing to consider for it. So how does this EDA visualization that we're trying to build here support our project goals? Well, we mentioned that we're trying to predict ignition locations and that we have satellite data to do that, to monitor and track the movement of these fires that we've now identified with this clustering algorithm. And then the key really is going to be to understand the patterns among and between those variables that contribute to the initial ignition and the continued spread. This is important implications for resource allocation and future assistance for, say, the fire stations, as well as keeping tabs on problem spots or when the weather changes and things like that. So let's just back up a second. So I'm a data scientist who doesn't work with spatial all the time. How did I get the state of Victoria on a map? And I was able to do so with just a few lines of code here. And so this is the map on the right that the code on the left gives me. And so some of this might look familiar. So I'm using just ggplot2. And this library, Our Natural Earth, contains vector geometry representations of different countries and states within those countries around the world. So it's really handy if you don't want to have to go look for a shapefile and things like that. And when I say vector data geometry, what I mean is everything starts with points, so lats and longs, and then line segments that connect those points. You can then build geometries. You can see here that the coast of Australia gets pretty detailed in the points that we can plot for them. We then have two. So once I have my Australia object, I'm just saying plot it. I'm then using this thing called geom_sf. And so what this does, I returned Australia as what's called a simple feature object. And this has become really handy for working with spatial data. Essentially gives you a tidy data representation of your spatial geometry. And so let's take a look really quick at what am I doing here that I'm capturing Australia this way. Let's look at that Australia object. What we have here is it's telling me that Australia is a simple feature collection. And what that means is it's really a combination of those points and those lines and those polygons that make up the shape of the country. I also have information on attributes. So in this case, the name of those states, as well as a list column of the simple feature geometries. I also just want to point out that native to Our Natural Earth is the coordinate reference system. And this has to do with how the country is projected onto the map, and it's just important to note. And so the WGS84 datum here is a pretty standard one that's capturing a definition for the Earth's shape as an ellipsoid. So I could give an entire talk on that, but I won't. So I just want to focus on sort of what this gets me and what does it mean to be a multi-polygon. The SF package has some really great vignettes explaining all of this stuff. And so some of the key geometries that you might see, again, starting with really simple points, latitudes and longitudes, you can connect those into lines. And in this case, the reason that the states are multi-polygons is because you can have like different cutouts or little islands or things that need to be captured. So once I know that I can work with this like a tidy data set, I can then just filter to get Victoria to where the name is Victoria. And then that geom SF piece of my code knows to look for this geometry column and plot whatever is there. And so that's super handy and pretty quick to get up and running. So now we got Victoria on a map. So I just filtered to, again, where that attribute name is Victoria. I include the geom SF piece here. And then instead of using labeling latitude and longitude like I did before, the theme map from GG Themes gives you a really nice clean outline of the thing that you're looking at. So at this point, the questions of interest and how you choose to use that shape is going to inform what you're actually looking at. So before I looked at the spatial distribution of fires over time, and we can start to answer some questions there, you may also be interested in the trajectory of individual fires. And so in this case, that map background is really just to anchor you in space, although you don't necessarily know what is there. So I know, because I've looked at a lot of these plots, that, you know, in this corner we have the forest and more rural areas. And then we can look at things like, you may be interested in the individual trajectory of one of these fires that we created. And there are tons of clustering algorithms to compare trajectories and things like that. It is all going to depend completely on your goal and what the question is that you're trying to ask and answer. So I mentioned that we have tons of data available to us to work with here. And so I just want to mention a few of those sources and why this problem becomes complicated for visualization. So we have the hotspot data. We also have the fire stations. We have information on daily weather. So things like the temperature, wind speed, solar exposure, was there rain? OpenStreetMap provides us with representations of roads and things like that. So we can compare how far is a hotspot to a road, which gives you a sense of, you know, rural versus if it's farther away from where people can reach it. Historically, as I mentioned, we have the origin of fire, what might have caused it, whether it was accidental, a lightning strike, information on recreation sites, or maybe people have campfires, as well as the fuel layer. So these are things like brush and plant types that may catch fire, as well as their coverage for an area. And then again, our fire movement. So when you start to think about the data structures you can build with this, the very first one is just that we have for every hour, as I mentioned, the fire ID, we have its location, things like firepower, the distance to the nearest fire station. CFA stands for Country Fire Authority, as well as the nearest one, how far it is from a road, all of these sorts of things. And then you may be thinking, well, maybe it's actually better to characterize each of those fires with summary statistics. And so instead of looking at its trajectory hour over hour, maybe I want to know things like how long did it burn? How far did it go? Where did it start? And how close was it to people and things when it started? What is the maximum firepower it reached? And then if you're, depending on your application, you may also decide to associate those fires themselves with a geographic entity. So in this case, maybe the CFA. And so this is where I had previously mentioned resource allocation. It may be helpful to know which ones are getting overwhelmed with fires in their area. So as you start to think about all of the data that you have available and all the variables that are there, the more questions you start to ask and the number of potential plots increases to infinity. And this is where it is so easy to get complete analysis paralysis, because especially once you get a map involved, it's like you want to do all of the things to sort of capture everything that might be interesting. And it turns out that just kind of slowing down, going back for a second, keeping in mind who is the audience, what do you want them to know, what might appropriate graphics be, and is user interaction going to be helpful? It helps you focus, I think, on one of these data sets to think about. And it turns out that you have 3 different ways of thinking about your data here, but they ultimately really come down to the same data structure. So essentially what you have is an ID column, which is your key. You have a time. This can be a constant step, like we had hour, or it could be ragged. You know, maybe if we had looked at the fires over a different time period, it could be inconsistent there. S1 and S2 are sort of like your location, your Latin long, if you will. And then V1 through VK are all associated variables that you have. And so from that data schematic I showed before, you really can append variables of interest from those various data sources, all associated with, for example, a fire and an hour, or a CFA and a day or a week, or whatever the case may be. And so now once we have a generalized data structure, it's more helpful to think about kind of what are the analytical tasks that you're going to answer, and this will inform the types of visualizations you make. So in particular, what we really want to know is where are events happening in space and time? And is there an association between a variable, a place, and the time at which it's happening? Components of these tasks, you can take a variable and map it to a color or a point on a line or a map. You can look at a time series where you're looking at the variable across time by fire in this case, or you can summarize them. And this is where, too, I think it's so easy to start to think, I want to, you know, map something to color and something to size and something to shape. And at some point, that becomes unhelpful because you're just overloading the viewer, and really picking apart the pieces you want to look at can be really tricky. So simple in this case is better, I think. And this is where Wilkie has a really great book that you can view online, where it talks about good and bad data visualization aesthetics. So sort of going back to first principles. So now I want to look at how do you interact with your data, and I have two ways that I'll show. Again, keeping it simple, building upon layers. One package I've really been having fun with is TMap. And so you can set up an interactive viewing modes that we can get for free a little bit, sort of what is where within that state of Victoria map. And so here all I'm doing is I'm converting my data frame of initial ignition locations to an SF object. I'm setting sort of a base layer of what I want the image to be. We can look at, I'm just then adding on the same Vic object that I had before, which will be the shape. And then I have now, I'm just plotting the active hours as the shape, the size of a bubble. And now, let me just pull this over here. And so what this allows us to do, I've faceted, so you can now look at essentially those 6 plots that I had before are now interactive. So I can zoom in, and now I have a nice view on the fact that over here is all forest. I can see where those fires are occurring month over month, and just a sense, too, of where they're happening. And so, of course, the ability to pan and zoom is really fun, and I love that it keeps track of where your mouse is in one window compared with where it is in the rest of them. I'll also just briefly mention, so I really like making shiny apps. Let me go back to full screen really quickly. And this is where linked plots can also be very helpful in keeping it simple. So I'm just showing here fires that started at the same time on a certain day that was pretty bad. And so I'm going to have the location of those fires on the Victoria map, and then a time series below it of the firepower. And so I just wanted to show in the code here that this stays pretty simple. So we have just a basic ggplot, and then I'm just using Plotly and really wrapping that. And the linking part is done with this highlight key. So I'm saying that to combine them, we're going to look at the fire ID, so that when I brush on one thing, it will be highlighted in the other. And the types of things this inlet allows you to see that is quite handy is I can consider, does firepower change depending on the location? So if I look at these 2 fires, I see that firepower stayed low, and they didn't last very long, compared to what we know is over here, more of a that forest area. These last for a lot longer. The firepower gets higher. They have more opportunity to burn. And if I had time, I would quickly change the color on this, and distance to the road, you see that these are much farther from the road. And so there are some interesting patterns to be seen by being able to brush and have representations come up in a different plot. A couple of fires over here, we see they last longer, but they never get particularly hot. So I might then want to go look at what was the weather happening in those areas. So I just wanted to mention some talks and books that I found helpful as I've been thinking about this. Again, the key points being keep it simple, use what you know, and just be aware of learning a little bit more about simple features and things like that. We had a really great Mappy Hour, we called it, with Our Ladies New York City a few months ago, where we had 2 great talks by Ayanthi Gunawarnana and Angela Lee. Geocomputation with R has been a really great online resource, and documentation for the packages I mentioned are just fantastic. It may also be that Shiny in particular, like at some point just can't handle the scale of data that you're sometimes working with. So I also just wanted to point out 2 solutions outside of R that give a nice scalability piece to spatiotemporal data. The first is NanoCubes, which was developed by some of my colleagues at AT&T Labs and allows for really nice panning and zooming with time series representation below. And then Uber came out with Kepler GL, which is also really neat to work with. So those are nice extensions if R kind of hits a limit somehow. And so once again, I just want to thank so much Dai and Weihao for all of their help and work on this project, as well as ACEMS for funding my work with them. So thanks so much.
Thank you, Emily. GIS is so popular nowadays. We just had a workshop this week as part of the workshops with Kaz Sakamoto doing a whole day of GIS. And last year we had Edzer.